Hi guys, and welcome to today's video. In today's video, we're gonna see function pointer in C. First of all, we'll start by setting up our STM32 based project. The STM32 microcontroller will be used to demonstrate the different concepts and theory that we're gonna learn across the different slides. We'll see how we can define our function pointer and the main syntax to be used to properly define and declare this function pointer in C. We're gonna see as well how we can initialize properly the function pointer and how we can utilize it for indirect callback invocation. And finally, we're gonna conclude today's video by two concrete use cases on how we can deploy function pointer for driver abstraction, as well as how we can deploy function pointer for state machine and command line design pattern. The hardware to be used across this video will be the STM32 L4 microcontroller. This Nucleo board based microcontroller will contain an ARM Cortex-M microprocessor. And the whole idea behind using this microcontroller is to demonstrate at device level the impact of using a function pointer and how the function pointer is working in reality at hardware level. Now, to build your project, we'll need set of tools like the make as well as the compiler. All the necessary tools will be provided as part of the Wadix technology tools GitHub repository. Finally, the makefile based project itself will be located as well as part of the Wadix technology GitHub repository, and this is the full link to the project. All those links will be provided within those slides as well as part of the video description. We'll need now to clone and check out our Wadix tools GitHub repository under C drive. My recommendation is to pick up C drive because it offers short paths to the different tools and applications to be used out of our tools directory. Now, in terms of tooling, our Wadix tools GitHub repository offer quite big number on terms of toolings and applications. Nevertheless, for our makefile based project, we'll need mainly the ARM GCC compiler. This is the ARM non-EOB GCC compiler from ARM, and this is targeting mainly the ARM Cortex-M microprocessors family. Our makefile project will be an ARM Cortex-M3 based project. Then we'll need this GNU Win32. This one does contain already our GNU make build tool. And finally, we'll need set of tools and applications to be used in combination with our make file. So those applications will be used as part of our makefile rules to create directories, remove directories, copy files, change or modify existing files, and so on. Cwin64 does provide those set of applications. Example, we can create directory via this mkdir application. We can remove via rm as well as rmdir for directories, and so on. Now, we'll need to set up our Windows environment variable path to point to those applications and tools. Hence, the Windows system will be able to recognize the location of those tools and applications once they get invoked via the command line. For that, I have prepared this PowerShell script install environment. Once executed from a PowerShell session, then the Windows environment variables for the current account will be updated to point to our applications and tools needed by our project. If you want to revert back, then you can use this an installation environment PowerShell script. So this to install, and this is to restore back the old paths. To execute those scripts, you need first of all to open a PowerShell session. So like this, as you can see. Then the first thing to be done within the current active PowerShell session is to enable the execution policy. This one enables PowerShell to accept external scripts and execute them. Without running this command, the PowerShell session will block the execution of our PowerShell installation script. Once we executed this set execution policy, we can navigate to our tools directory. Then we initiate the execution of our installation PowerShell script. Once done, the Windows environment variable path will be updated and pointing to our applications. So if we inspect the environment variable of our account, then we go to path. As you can see, the path has been updated to point to our Segwin64 applications, as well as make build tool, as well as the ARM GCC compiler. If you want to revert back, then you can just execute the uninstall PowerShell script. Now, if we inspect again, as you can see, the previously added tools has been removed. Now, I will just execute again this install PowerShell to be able to move forward within our makefile based project. As you can see, this has been added again. Now we can move forward and check out our makefile based project. Function pointer in C, in terms of definition, is quite similar to the standard definition of normal variable pointers. So function pointer is just an address memory that contain the address of another function. Each function that has been declared and defined within our C code will be allocated an address. We can directly invoke this function within our C code, or we can use a pointer to indirectly invoke this function. To make our pointer pointing to this function, we will need to initialize the content of the pointer address with the function address itself. So as you can see, this is the pointer address itself, and this is the content of the pointer address. And this content will be corresponding to our function address. Now, in terms of syntax, the function pointer should follow the function signature itself. You need to keep in mind that the function pointer will be used to point to standard C function. And any function within C or even C++ will have a unique signature. A signature consists of the function return data type. So this is the return value data type coming out of our function, as well as the data type of the different input parameter of our function. Hence, if we are going to declare and define a pointer pointing to our C function, then this pointer or function pointer must utilize the same function signature. Hence, you need to specify the data type of our returned value, and this one must be matching the same data type of the function that we are going to point to. Then here you're gonna create the name of your function pointer, and of course you need to specify this star. This is to say this is a function pointer. Then you need to specify the same input parameters data type as the function that we're gonna point to. With this, we'll be able to match the exact function signature that we're gonna point to. Any mismatch in terms of function signatures, like mismatch of the data type of the return value of the function that we are pointing to, or mismatch between the data type of the input parameters of our function pointer and the input parameters data type of the function itself that we are pointing to, will lead to unpredictable behavior. And sometimes the compiler will be able to spot this mismatch and will fire either a warning or a compilation error. You don't need all the time to specify the data type of the input parameters or return value. This is really depends from your function. So if your function doesn't accept any input parameters, then of course your function pointer doesn't need to have input parameters. And same, if your C function is not returning any result or value, then the function pointer to be used to point to this function doesn't need to return any kind of value as well. Now here, this is a C code example to demonstrate how we can declare a function pointer and how we can initialize it to implicitly invoke a normal C function. So first of all, we'll start by creating our C function. Then we'll move to declare our function pointer. As you can see, the signature of this function pointer must match the signature of our C function that this pointer will point to. So the data type of the input parameters of our function pointer, as well as the data type of the returned value of our function pointer, must be the same as the data type of the input parameter. So this is the C code example to demonstrate how we can declare a function pointer, then how we can initialize this function pointer in such a way we can implicitly invoke our C function via function pointer invocation. So first of all, we have created our C function. Then we move it to declare our function pointer. As you can see, the signature of this function pointer must be the same as the C function that we want to point to. So the data type of the input parameters as well as the data type of the returned value of our function pointer must be the same as the data type of the input parameters of our C functions as well as the data type of the returned value of this C function. Once done, we'll be able safely to initialize our function pointer with this C function. Now, this is the syntax at C level. But what happened at hardware level is that the content of our function pointer address will be initialized with this address of our C function. So the address of our C function will initialize and be put within the address of our function pointer. With that way, we are pointing now to this C function via this function pointer. And hence, we can implicitly invoke the C function via the invocation of our function pointer. Now, as you can see, this is our makefile-based project and will be used to demonstrate how the function pointers are working at hardware level. So this project is targeting an STM32 microcontroller. Hence, the compiler, the compile flags, as well as the linker script is adapted for an STM32 microcontroller. Also, I have prepared two sets of examples to demonstrate how the function pointers are really working at hardware level. So the first C example will be used to demonstrate how we can declare a basic function pointer, then how we can initialize this function pointer in such a way we can implicitly invoke our C function via the function pointer invocation. And we will focus on what is happening really at hardware level when we are doing the function pointer initialization, as well as when we are invoking the function pointer. So I will start by compiling the project. Then we'll load the binary via Keil project. So everything will be generated within this build directory. So this will include the binary itself to be loaded, the disassembly file, the set of the object files coming out of the compilation, as well as the Keil project to be used to load our binary. So I will load the binary into the flash memory. Then we'll start a debug session. So now we are within our example, and we'll try first of all to explore the addresses of our function pointer as well as the address of our C function. So once we declared our function pointer, then this function pointer will be allocated a memory address, as you can see. So this is the address of our function pointer. And as you can see, it is not initialized, so it will have 0. Then this will be our C function. This one will have as well an address. This C function will be located within the text section. So this will be within our flash memory. And this is the address range of our flash memory. The function pointer, as it is declared as a global variable, it will be located within the data section. This means it will be located within the SRAM area. And this is the address range of SRAM within an STM32 microcontroller. Now, when we are doing the initialization of our function pointer, we're gonna initialize the address or the content of this function pointer with the address of our C function. This means that the address of the C function here will go to the address of our function pointer. So let's go. And here we go. As you can see, the content of our function pointer get updated with the address of the C function. Once we created this connection, then we'll be able to invoke the C function via this function pointer. So here I did an explicit invocation of our C function to get the first result. Then I will invoke implicitly the C function via this function pointer. So if I set a breakpoint here, then start single step, as you can see, by invoking this function pointer, I will end up in our C function. So we were able to implicitly invoke the C function via this function pointer. Then I run. Here we go. I am within the C function. Now let's compare the result. This is 1E in hexadecimal, and this is 1E in hexadecimal. So we're able to invoke the C function, first of all, explicitly via direct invocation, then implicitly via this function pointer invocation. Now, in terms of use cases, we can use the function pointer for C driver abstraction. In this case, we'll need to create a C structure that consists of set of functions pointers. And then this C structure will be once pointing to version 1 of our SPI driver, and in another time will be used to point to version 2 of our SPI driver. The version 1 or version 2 of our SPI driver will consist of set of functions that, in terms of signature, will be matching the different function pointers used to initialize our C structure. And hence, we can initialize our structure of function pointers with the different functions from the SPI version 1 driver. And if we need to switch and use the SPI version 2 driver, then we'll initialize the structure with the SPI version 2 driver functions. Another advanced use case of those function pointers in C is to implement a full state and command design pattern. In this case, we can implement a full model that exists within real life using basically function pointers. So first of all, out of the real model that exists or the real use case, we need to create a full state machine that consists of set of nodes and states, and the transition between one state to another will depend, of course, from certain prerequisites and conditions. Once we're able to modelize the full real use case using a fully featured state machine, we can move on to the implementation using our C language programming. The easiest way to implement this state machine will be via this nodes that consist of function pointer. So this node is just a representation of the different states of our state machine. So this state drive, neutral, and reserve must be encapsulated within this variable state machine. To do so, this variable must be of type state node, and this one is just a structure that encapsulates the name of the state, and then we'll have a dedicated function pointer to point to the real implementation of the state. Once we declared our global state machine and we ensured this encapsulation of the different states, we can move on to do the actual initialization. This means for each state name, we will assign the corresponding C function. This will be possible only if our state machine variable is flexible in such a way it can accept and invoke implicitly those different functions. And the only way to achieve this implicit invocation of different functions that have the same signature will be via a function pointer that share the same signature as those functions. Once we have initialized properly our state machine, then we'll have the full flexibility to invoke and move on within the state machine from one state to another via invocation of the corresponding function pointer. The only drawback and limitation of such approach is that all functions here must share the same signature. The type of the state machine is this kind of standardized here and can work only if our state functions share the same signature as this function pointer. If not, then we cannot do this initialization in proper way, and mostly we'll get a compile time error. However, if we respect basically this limitation and we're able to work with it, then we'll have the full flexibility to invoke any state of our state machine model without any kind of problem. And we'll be able to utilize the full runtime capability of those function pointers invocation. This will minimize, of course, the code size of our C code. And the code size is very critical for a limited embedded device hardware resources. The second example consists of demonstration on how we can utilize those function pointers to abstract the invocation of different driver API versions of our SPI. So the example consists of having init function which vary in terms of implementation from one driver version to another of our SPI IP. So we'll have two versions of this SPI init function. Then we're going to create an abstracted structure that consists of function pointer. And this is the signature of our function pointer. The signature must match the signature of those init SPI driver API. Out of this function pointer structure, we'll create basically two global structures. One will be used to point to our SPI init version 1. And the second structure will be used to point to our SPI init version 2. Then finally, we'll create a global abstracted SPI driver structure of type structure function pointer. This one will be used later on either to invoke the init API function version 1 or the init API function version 2. So one time will be initialized with this SPI driver version 1 structure, and another time will be initialized with this SPI driver version 2 structure. And the whole idea is that we need to abstract the invocation of those two different SPI driver functions. Hence, we can keep our testing scenarios kind of in abstracted way. Means, if we're gonna update the implementation of those functions, then we should not modify or update our testing example. We should have a proper abstraction and isolation between the top level software and the low level software. And the only way to reach this proper isolation is via structure of pointer functions. Now let's compile our example. Done. We'll go to our build directory, then open Keil project. Okay, Then we can move on to our example. Now, first of all, we're going to initialize the structure of function pointer with this SPI driver version 1 structure. This one is initialized already with our SPI init version 1 API. Now, if we try to invoke the init function via this structure of function pointer, we'll end up by invoking the init SPI version 1 function. Then we can move on. So this value will be 1, as you can see. And this is the expected result. Now we'll try to update this structure of function pointers with our SPI driver version 2 structure. And this one is getting initialized already with the version 2 of our SPI init API. Now, if we move on, here we're able to invoke the version 2 of our SPI init API via this function pointer structure. So here we instantiate this function pointer structure, then we specify our function pointer init, and this one is now pointing to this API revision. If we continue, we'll see that the outcome result is matching the returned value of our SPI init version 2 API.